Electrical fundamentals.
All right, so here's my suggestion, unless you guys really want to plow ahead. This is a pretty good stopping spot, and I'll bring worksheets and we can monkey through this in the next session.
Sounds good. Is this the,
For electrical fundamentals. Current, voltage, resistance, and power. Those are the 4 things that are required for electrical energy. Fundamentals of electricity. When dealing with electricity, what we're referring to is the flow of electrons through a conductor. Electrons are negatively charged atomic particles. They fly around in the outer shell of an atom. And some of them are easier to move than others, and those are good conductors. The opposite charge is the positive charge. That's in the nucleus. Flashbacks to high school, anybody? Conductor is a material that allows electrons to move with relative freedom within the material. So copper, aluminum is a really good conductor. It's horrible in your house because it corrodes. Metals are generally good conductors of electricity because they have many free electrons. Note the color. It's yellow. It's on the test. In electronics and radio, we control the flow of electrons to make things happen. So that's what all the little parts inside the radio do, is they control where they're going and when and how. You need to have a basic understanding of how and why we control the flow of electrons so that you can better operate your radio. That used to be a lot more true than it is today. In the old days, you could repair your radio. Today, unless you have a microscope and mechanically controlled tweezers and a fancy schmancy hairdryer called a soldering gun, you're not going to work on your radio.
And it's gotten bad enough, just to let you know, I've been repairing radios for 55 years. I take it for granted, okay? On that brand new, lovely TH9800 out there, I have a dead radio because it has failed to transmit audio. It'll do everything else, it will not transmit audio. I can see the problem on the schematic. I know where that problem is. Do you think I can find that thing?
Yeah, it's gotten crazy. We've got some examples over there of the old time stuff. Actually, it's not even the old time stuff. It's the newer time stuff. So you're not going to work on your radios. All right, we're going to try. Voltage is E. It's in volts, okay? So that's the 3 characteristics. That's one of them. Voltage is E, and it's in volts. Current is I. It's measured in amps, or the unit is amps. Resistance is R. And it's measured in that funny Greek letter, ohms, like a whole bunch of other stuff. And all 3 will be present for electrons to flow. If you don't have one of those, nothing's happening. Okay, so on the left-hand side, it's water, right? The flow of water through a hose is a good analogy to understand. So on the left-hand side, we've got a water system. We've got a pump. There's pressure coming out. It's being measured here. And the pressure is coming along, and there's the flow, and it comes back in. Okay, and this is the other side for the pressure because we're taking the pressure difference from here to there. The battery is doing the same thing. It's flowing through a current. So this is an amp meter, or ammeter, and it measures the current. Just like the flow through here, the current is the flow of electrons through this wire. For current to flow, there must be a path from one side of the source to the other side, a source, and this path is called a circuit. So source, or positive of the battery, and it's got to come back to the other side, or the negative of the battery. If you don't have that negative side, nothing flows. There must be a hose, or conductive path, or a conductor, the wire, through which the water or the electricity can flow for either of those systems to work. All right, voltmeter connected in parallel measures voltage. It's in yellow. So it's on the test. The ammeter connected in series measures current. You need to know that, but you don't need to know that for the test. So the question is, voltmeter connected in parallel measures voltage.
And the ammeter connected in series is yellow later. You will be testing.
Oh, it is?
Yeah.
Yes, ma'am.
What does it mean in parallel?
Did we not cover that?
Parallel is side by side. Series is in line with
I believe we cover it shortly.
Yes, we do.
Yeah, there's 2 different ways to wire something. Remember the Christmas tree lights in the old days when you were a kid, and one bulb went out and the whole string died?
Yep.
They were wired in series.
Oh, okay, now I get it.
Because one open light bulb opened the whole circuit.
So parallels just got the second wire to keep the flow to everything.
Yes, we'll show you some drawings of it in a second. A second, literally. So that is a series. If you break any piece of wire or the filament goes out, everything's dead. There's no current. There's no path.
You're done.
Yeah, that's your old Christmas tree lights. So it's a series circuit. There's only one path for current to flow. The current is the same through each component. So in a series circuit, the current is the same through each component.
Everywhere in that circuit, the current is the same.
And the current is the amperage. How many amps or millivolts or milliamps or whatever. Current, yeah, the component junctions is unchanged. All right, parallel circuit, the other way, multiple paths for the current to flow. So if I break this wire, this one could still light and that one could still light because there's still a path either way. So any one of those breaks, there's still a path for the other ones. And that's your modern Christmas tree lights that don't lose every bulb.
So if the R3 went out, then the R1 and R2 would still work.
They would still work. If R1 or 2 or 3 or 2 of them went out, there's still a path for the remaining bulb or bulbs.
And I'm going to toss one out here that you probably should ignore, but I'm going to toss it out anyway. If one of those lamps shorts, they all die. But you also blow the fuse, so life is good.
Okay, multiple paths for current to flow. Parallel circuit, the voltage is the same across each component. Current at the junctions is divided between the components based on their values. So the voltage is the same at all points, but the current is divided. So if there's 100 amps measured flowing from there to there, there's going to be 33 amps at each one of those. Okay, the current's the same is divided, okay? But the voltage is the same across all components.
I didn't get that at all.
Okay, voltage is the electromotive force, okay? That is potential.
What's the component? Just the section?
The light, the wire.
This is the component,
Thank you.
component.
Characteristics of electricity are interrelated. Is this where we get into,
Yes.
you're gonna love it. We get some math coming up. Voltage, current, and resistance must be present to have current flow. That's a basic concept. I don't know why that one's not in yellow.
It should be.
It's not in the text.
I know.
Just like water flowing through a hose, changes in voltage, current, and resistance affect each other. So if you put your thumb over the end of the hose, it increases the pressure, right? The effect is mathematically expressed in Ohm's law. Voltage is measured with a voltmeter. So we have voltmeters, we're going to probably tell you, ohm meter is the next. Current is with an ammeter, and resistance is with an ohm meter. You go down to Harbor Freight, this is one of the expensive ones. I think this was $30. But for 15 bucks, you can get a meter that does all 3 of those. Instead of buying 3 separate meters, you buy one of these, and it'll suffice for most of your needs.
They'll do all 3 of these,
Either of these cheap little things will do all 3 of those for AC and DC.
Be careful what you said at that, though.
Yes. So if you set this on DC and you measure a wall circuit that's AC, it's going to say 0.
So those are multimeters?
Multimeters. But that's not up there yet in yellow. But that's what they're called. A voltmeter is an instrument that only measures electric potential. Okay? So your battery's nominally 12 volts. You stick that on there, and if it says 12 volts, you need to charge your battery because that's discharged to 50% depth. It should be up around 13, but this will tell you. And that's only an indication of the health of your battery. Multimeter, single unit that allows you to select which of the 3 basic electrical characteristics to measure. And they're really cool. You set it on a beat tone, and you put the probes on the 2 ends of what's supposed to be a circuit. And if it's got an open in it, it won't make noise. And if it's the complete circuit, it'll go beep, and you know you got continuity through there.
Especially useful for fuses.
Very useful for fuses.
It's actually easier to understand this when you're working with batteries. I mean, the parallels.
Yeah.
Thing,
Yeah.
because you can measure it.
easier?
Well, it's like when you put all those AA batteries into some component and you got to stack them all up and there's rows of them and they're on top of each other. Well, the rows are series and the stacks are parallels. They could be connected at the top, so you have a row here and beside it they're all electrically in series. And then on the other side another set that's in parallel.
But you can measure the voltage then, and
Yeah.
find out, you know, that 1.5 volts for the cell.
Well, it depends on the battery. So, yeah. We'll get into that when we talk about the Baofeng handhelds and the accessories and stuff. Power is watts, and a watt meter is also called a power meter. All right, precautions when measuring. When measuring in-circuit resistance with an ohm meter, ensure the circuit is not powered. So when you're measuring resistance, you don't want electrons flowing through there because it'll flow through your meter and hurt it and possibly you. When measuring in-circuit resistance with an ohm meter, ensure the circuit is not powered. You did that?
I did that.
On the sub?
No.
Okay.
No, I did it with the cheap Harbor Freight. And it was toast.
You know, there's a good use for Harbor Freight stuff. I'm not sure this is going to blow up my test equipment. Let me go to Harbor Freight and get a $5.
Buy a cheap one, sacrificial.
Okay, be sure you're on the correct setting before measuring. For example, attempting to measure voltage when using the resistance setting can damage a multimeter. That's kind of the same question.
Yeah.
Pretty much. If the multimeter's on the wrong setting, you're going to hurt something. It, you, or the circuit.
Unless you have a smart multimeter that just says no.
Some of them will actually say error and give you an error code, and you go, if you still have the book, go look up the error code and it'll tell you what you did wrong. Precautions again. Think about what the readings mean, okay? Think about what the readings mean. You need to know what you're looking for, or you need to take a measurement and then go figure out what that measurement's telling you. So here's one of the things to be careful of. A large capacitor in a circuit being measured with an ohm meter, okay, might initially indicate a low resistance and then show increasing resistance with time. That's because it's charging up.
Which makes it dangerous. We'll more on that later.
Yeah, we'll cover that in more in depth. But yeah, it's like, there's no resistance here. How come it's climbing? Don't bang the digital multimeter on the thing and see if you can straighten it out. To measure voltage potential, the voltmeter should be connected in parallel. Okay, not in series, in parallel. So you don't take separate the wire and put the leads across it. Okay, that would be in series. You measure it in parallel. When configured to measure current, it's in series. So you would hopefully not have to cut the wire. Take a circuit off and put the wire across. You can't measure a lot of current with these digital multimeters, but there are other pieces of equipment that you can put in there that will do that. When configured to measure current, a multimeter is connected in series. Okay, voltage parallel, current series. AC and DC waveforms. Direct current, or DC, is current that always flows in the same direction. It could be going that way, it could be going that way, but it ain't going to change. DC voltage is voltage that always has the same polarity, so positive or negative.
One or the other?
Well, you have both.
Depends on where.
We typically tell people it flows from the positive and then it flows through and comes back to the ground through the negative to the source of the battery. Okay, so it always goes one way.
And realistically, that is wrong.
Shh, don't tell them. We'll confuse them. I know, that's why I said it the way I said it.
The chart in the book shows it kind of like stops and then
That's AC.
That might be, AC should.
it goes the same way, but it stops.
Do you have it?
Anyways, go ahead. I might.
Okay.
That was one question.
Okay, so DC voltage battery has the same polarity batteries in most electronics. Okay? So you plug it in the wall, but it changes that to DC generally. And then sometimes in there, it's going to change it back to AC for certain things. Alternating current, okay, AC, is current that reverses between positive and negative directions of flow. So it's going this way, completely stops, because you have to stop in order to go the other way, and goes the other way. completely stops and goes back. It's alternating current. It's going that way, it's going that way. And our electrician's going to smack me if I say it wrong. No? No, I'm not saying that I said it wrong, but if I do, you'll correct me, right?
I wasn't paying attention.
Oh, man! Okay, so it's flowing that way with a certain amount of amperage, right? Current. And it's got to stop and go back that way, and stop and go back. So part of the time it's stopped, and there's no current, and that allows infinitesimal portions of time for the conductor to cool.
This
Cycle is 60 hertz, generally.
how many times does it?
60 times a second.
60 hertz, 50 in Europe.
Okay, yes, 50 in Europe. What is it on the sub? I know you know.
60.
It's 60. AC voltage. AC voltage is voltage that changes polarity, goes back and forth. Your household wall circuit or outlet. Polarization in yellow. The orientation of the electric field of a radio wave defines its polarity. So the
The
orientation.
key word here is the electric field. There's more than one field you're going to deal with.
Yeah. Because we've all heard electromagnetic radiation. There's two components there, electro and the magnetic. So the electric field defines polarity for the radio wave. Okay, wavelength. So that funny little attempt, Windows has a issue with trying to do an actual lambda. So in the pictures that we're going to see, there's a little curl up there on the top of that thing, but it's a lambda. Lambda is the symbol for wavelength. C is a constant, which is the speed of light in a vacuum. Okay, hold on, we got to go back. So what's the speed of light? We all live in the United States, so the speed of
Million meters south of
3 times 10 to the 8th.
Or 300 million.
Or 300 million. What unit?
Meter.
How often?
Second.
That's correct. A lot. 3 times 10 to the 8th. Okay, so let's go back to it. It's not 186,000 miles per hour.
300 times 10 to the 6th.
It's 300 times 10 to the 6th. It's 3 times 10 to the 8th.
Yes.
Did I say 300 times 10 to the 8th?
Yes.
Oh, my bad. Okay. I don't have 300 or 3 up there, do I? Okay, so 186,000 miles per hour or per second is hard math. But 300,000 or 300 times 10 to the 6th, there's just a bunch of zeros you can get rid of. So it makes the math easier.
And the metric system really does make a lot more sense.
It does, and they promised me in the 70s that we were going to it, and here we are 50-something years later, and we're not. And it sucks, because it's a whole lot easier. Frequency, the little f, is frequency in megahertz, okay? And then down at the bottom in red, because it's not on the test that way, lambda, the wavelength, equals c divided by f, which is the speed of light divided by the frequency in megahertz, which equals 300 divided by the frequency in megahertz, because megahertz has a bunch of zeros on it as well. So you get to knock out a bunch of zeros, and it makes the math a lot easier. So it's 300 divided by the frequency in megahertz. So 2 meter, we're on 146.0. 300 divided by 146 gives us roughly 2 point something. It's a 2 meter band.
And the reason that's important?
Because I said so.
That won't work.
Because we deal with the spectrum in bands. So 2 meters, 20 meters, 40 meters, 60, 80, 120 meters?
And why is that important for
160.
radio? Why is that important for radio?
Figure out where to
To stay in the rules, is about the only
It's
reason.
the antenna that you need.
Well, okay.
How long you cut your elements on.
Right. Yeah, every frequency requires a different length of element, but you can get a wide section of a spectrum with one length of an element.
So wavelength is measured in meters?
Yes, the wavelength is.
Yeah.
So you need a certain length of your antenna to.
We will cover it in depth, but yeah, you cut your antenna, if you're building your own, to the length, that the wavelength you're going to operate on requires.
So you can't have an antenna to listen to the whole thing?
Yeah,
Well,
listening's
we're gonna get
easy.
really carried away with this whole subject later.
Yeah, we got a whole series on antennas.
But the important thing is why we're doing this is so that you can understand, it all comes down to antennas that you're going to need to transmit on, basically.
Right, so we'll get to the antennas.
Multiple antennas, what you're saying?
Yes.
There's not a one
There's all
size
kinds
fits
of-
all?
There is.
Not a one size fits all, but there is a one size that fits many.
Okay.
And there's one size that fits pretty much all fairly well, but every antenna is a compromise as soon as you say, I want more than just that exact spot. If I want to go 10 megahertz over there, now I'm compromising somehow.
And in a really basic sense, think of an antenna as like a tuning fork. It's going to be resonant at a certain frequency. And with these, it's really going to vary with the element lengths.
But we're going to get so far deep into antennas that you'll know how to build your own. But we're going to do that later. So
And the goal is to get you to understand the antennas that are commercially available first, and then build your own, because they're not
Right.
happening.
But the reason for all of this is because we're going to have
the basics. This is the basic formula you're going to use to when you do, if you do build an antenna, and you need this formula in the test.
or if you're going to buy one.
Or buy one, yeah, because we'll teach you about the lies and the misleading marketing and things like that when we get to the antennas. Okay, lambda, wavelength, equals speed of light divided by the frequency, or 300 divided by the frequency in megahertz. And this, that's not very big. Does that blow up on the next one? No. Okay, so a little squiggly line there going to the lower right. That represents the wavelength. The distance from the trough to the trough, or from a peak to a peak, is the wavelength. That's one wave, okay, up and down. That's for 2 meters, that goes up and down in a little over 6 feet.
And you can't see the text. What that says is distance the wave travels during one cycle.
Right here. So it does
Any point in there can be equivalent to the same point on the next cycle. That's one cycle. You can think of it however you want to do.
Right.
Wherever you want to move that to create one cycle in your mind, do it.
Yep. The frequency is the rate at which voltage changes polarity or current changes direction. Just memorize it. The frequency is the rate at which voltage changes polarity or current changes direction. The unit of measurement for frequency is hertz. You can remember this because Hertz has a high frequency of their customers being arrested for stolen cars. Hopefully that sticks in your mind somehow. So yeah, Hertz has had a few customers that got arrested for driving stolen cars that they mistakenly reported stolen or didn't unreport stolen. They were sitting in their lot and they thought they were stolen. They rented out to the next guy and he gets pulled over in another state and his vacation's ruined. So if that helps you remember that Hertz is frequency, we're good. All right, 1 Hertz is 1 cycle per second. If you hear people saying kilocycles or cycles, it's the same thing. It used to be called kilocycles, now it's called kilohertz. 1 cycle per second is 1 Hertz. Our electrical energy in the walls is 60 Hertz. All right, decibel. Oh, who's the math guys? Who's the math people? You're honors student, you got to do math, right?
Not for a history degree.
Liberal arts. Don't say history. It's liberal arts degree, right? I got to pick on it. I got to pick on it. Hey, I went to a liberal arts school.
You went to a liberal arts school.
I went to a very liberal arts school that hated my guts. Okay, decibels is logarithmic. So, but
Yes, you have to do math in order to get a degree.
logarithmic equations.
Some,
So you're the one that's going to answer these questions for the class, right?
sure try.
Yeah. We're going to teach you how to do it with one hand and your 5 fingers. Decibels, or dB, small d, big B, measures a ratio. It's a logarithmic scale. So a logarithmic scale, you've got a linear scale that's just a straight line going up or down, whatever it is, but it's a straight line. Then you got exponential, which gets steeper and steeper. Then you got logarithmic. So logarithmic power ratio. dB, or decibels, equals 10 log 10. P sub m divided by P sub reference. But we're showing you this and the 10 log 10, because there's also 10 log, or 20 log, 20 log 20 or 10 log 20?
Keep going, next line.
Is the next one? Ah, voltage ratio. This decibels is 20 log 10. V sub M divided by V sub ref. So you do a 20 log 10 of V sub M divided by V sub ref.
So voltage winds up being an entirely different critter than wattage.
So this math is horribly complicated in school because you got to do it to significant digits. But guess what? We don't have to.
Don't let it ruin your day.
No, absolutely.
One five-fingered Marine Corps, we used to use another name, but we're politically correct. It doesn't work anymore. One five-finger calculator. That's all you need. Maybe two if you got an amplifier or something. The M is for measured power or voltage, and a ref is the reference or known power or voltage.
Everything has to have a starting spot. That's your.
But there's nothing yellow up there yet.
If you don't know it, you're not gonna get anything else.
Huh?
I said, if you don't know that, you probably won't get much else.
No. We're going to teach you the trick.
Yeah, but tricks aside, if you don't understand the why,
Right, yeah. Well, that doesn't tell anybody anything unless they go, okay, what's a log?
There's a difference between power and voltage, that's what that says.
Yeah, and this was never really intuitive to me, but once you get into it, you just have kind of a working understanding of what you're doing. And the mathematics behind it can actually vary some people, but don't get that far into it.
Don't worry about the math. The math is down to 2, and that's it. You just got to double or half. 2 and half. That's all you got to know. Double it or halve it. Well, we're going to show you that. So you can refer to your book, T4, Chapter 8, G4, Chapter 3 and 4. dB, important. A very useful value to remember is that anytime you double the power or cut it in half, there is a 3 decibel change.
and this is important.
That's in the test, and that's how you're going to do any of the math questions about power.
And it's how you will evaluate every antenna you ever use.
Yep.
And or radio.
And or radio.
If you're going to write anything down today, that's what you want to write down. That's anytime you're playing with a radio, that can come into play.
My understanding, so 3 decibels, no other, if it's cut in half or it's not cut in half, it's 3 decibels.
3 decibel is always a power of 2 change, whether it's up or down. And what that means to you in a practical sense is if you put 5 watts down the wire on a 3 dB antenna, you are effectively radiating 10 watts.
Yeah, if I have 10 watts in my radio, okay, and I want to up my power and double it, that's 20 watts. Well, that's just 3 dB. If I cut it to 5 watts, that's halving the 10, and that's 3 decibels.
Minus instead of plus.
Negative, right.
Okay, so one is adding and one is subtracting. For the half it's subtracting.
Right, yes.
Half is subtracting, 3 is adding.
3 decibels is 1/2 of the original, or 3 decibels positive is doubling.
A minus 3 dB will always cut your value in half. A plus 3 dB will always double your value.
Okay, so whatever the value is, then if it's a plus, it's twice that.
Correct.
Right.
And if it's a negative, it's half
Correct.
Per 3 decibels.
per 3 decibels.
So if you got 9 decibels, you
3
That's
decibels.
double, double,
you
double.
double the
So it
10.
would be triple.
No.
No.
No?
No, it's double, double, double.
You double the 10 to 20. You double the 20 to 40. You double the 40 to 80.
Oh, okay.
And this is why we tell
That's
people
why-
specifically, you are way, way better off putting your money in a good antenna than in an amplifier. Because a good antenna is literally your savior when you get on the air.
So every net that I close on Friday night, antenna, antenna, antenna. If you buy a $5 antenna and put it on a $10,000 radio, you have a $5 radio system. I was out in the mine yesterday with 8-watt Baofeng, and I made it all the way to King Mountain from basically the California border because I had a nice antenna. Okay, so clear as mud, right? 3 decibels is a cut in half or a doubling, okay, of power. Okay, so here we are. 0.5 on the power is minus 3 on power, and 1.995. Double is good, close enough, right? okay, for the power.
Yeah.
Okay, we'll read decibels when we study antennas and feed lines. Study the manuals and play with the calculations on your calculators to get comfortable with this topic. On to questions.